Hello my friends, this is alternating current still, lecture 25. What I want to focus on here, how alternating current works in household and understanding the hazards of alternating voltage. This figure here is showing a battery producing a constant EMF, so a flashlight has a constant glow, but electric distributed in homes is different. Rather than a constant EMF, it has a sinusoidal variation. We talked about this. So the picture is a picture of a string of LED mini lights swung through an air which flashed 30 times per second. And LED light bulbs are on when the EMF is positive, but not on when the EMF is negative. There's a device we use to drop the negative part of the induced current, induced voltage, called diode. Actually, it is what we use to build these LED lights. And they're only on when we have positive current. So we have flashes, flickering flashes for LED lights, but they are fast, so we don't really see them flashing. If we slow down a video, we can see them flashing. Go ahead and try that. In household electricity, we actually have generally power fed into our system. That would be incoming power, and then we have our devices connected and grounded to protect harm if there's any electricity leakage. And this figure is nicely showing how we have our homes. Actually, we generally connect our devices in parallel. So as I connect my device here to a switch, I complete this parallel arm here, and I have a circuit that works for me. The other circuits are still not complete, so there's no current going through until I put another device here, and then the circuit is also complete, and so on. So the more and more devices we connect to the outlets, the more and more current we draw, because as you folks remember, hopefully from parallel arms, if they have the same resistance, they will have the same current, but they always have the same potential difference. So they keep drawing more and more current as we add more and more devices to the system. So sometimes our system could be overloaded, and the current could cause a fire hazard. Because of that, we have what we call fuses that goes off when we have too much current drawn from the power source. And of course, we have grounding to protect any electricity hazard when we have a leakage and so on in electric system. The smaller plugs are here called hot sides, and is where the electricity comes out in, current comes in, and the other side is called neutral side. It's where the current goes into the ground. This is another figure showing the same idea and listing more simply what I talked about. The more devices we add, the more current we draw, and to prevent fire hazard, we have circuit breakers, and to turn off the circuit if we have too much current drawn. Then we'll have to reset them. This is just about kilowatt hours. This is how electricity energy is measured. It's actually coming from here. We know power unit is watt, right? And energy is in joules, and seconds is the time. Energy, change in energy over change in time, or energy per unit time, is the power. So the watt unit is equal to joules times second. Kilowatt hour is when we calculate the energy from here, delta E will be equal to power times delta T. So unit is joule, and power has a unit of watt, time is second. So joule is equal to then watt times second. This is actually joules per second, sorry about that, divided here. So kilowatt hour is a different unit of joule. To convert this to joule, we convert simply kilowatt to watt times 1000, and hours to second times 3600 will have joules. So we can directly convert from kilowatt hour to joules by using 1 kilowatt hour is equal to 3.6 times 10 to 6 joules. We can use that to convert. And over here there are some examples of how much power a device draws, how much time, and how much energy it spends. So 200 watts of power, 5 hours, it will spend 1 kilowatt hours of energy, and so on. And here is how our energy is calculated, and we are charged in terms of kilowatt hours. Biological effects of AC currents are dangerous because of this change in nature of the current. Our body cannot adjust to it ever, and they can harm us a lot easier than DC currents. This table here is nicely listed. Threshold value of sensation, we feel some annoyance at 1 milliampere AC, 3 milliampere DC. Paralysis of respiratory muscles happens at 15 milliampere for AC, 60 for DC, quite a large difference. And a heart fibrillation fatal effect starts larger than 100 milliamp for AC and 500 milliamp for DC. We can form resistances across our body. There are overall, it varies by people, but overall we can show the resistance of skin, arm, torso, and legs, and represent the human body as a resistor system. And when current comes in, it will pick the easiest way it can, depending on the situation. It can go this way, or it can go that way, or it can go right across if it has the mean. So we will overall have a series circuit if a human body is connected to a system. If our skin is dry, we have 1 mega ohm of resistance, which is pretty good. If it's wet, it's less, it's 10,000 ohms. So this question here is about a worker who by mistake touches to a wire that has an electric leakage. And a very big mistake he has is to touch to a conductor that is connected to ground. So what will happen here is current will be able to complete its path throughout his body across towards the here. We'll have a complete circuit. He touches a high potential here, right, and a low potential there, which is 0. Overall ground potential is 0 volts. Current will flow. And the high potential he touches 480 volts. The question is asking us so he touches this 480 volt AC supply. His other hand is holding the metal railing. Skin resistance of each hand is in full contact with conductor is 22,000 ohms. So this guy is given here. This is actually 2200, I believe. Yeah. Too many zeros here. What is the current passing through? As he touches, here is the circuit that forms, passes through his torso, and so on. And what we do is find R total, add all the resistors across, resistances, and find current using delta V over R total. And here's what delta V is, right? He has high voltage here, low voltage there. This is like he is connected to a very high power supply. With delta V is equal to 480 volts. And here is the solution. We add all those currents, resistances across, and solve for current using 480. 95 milliampere we will find, and that's pretty much in the danger zone. So definitely some permanent damages will happen. So that's human body, and that's how it affects us. To protect, we have many systems. As we talked before, we have circuit breakers to places where it's wet, in kitchens and in bathrooms. We have what we call a ground fault interrupter. It's a system here that breaks the current. Suddenly, if there is an outgoing current here, I, it measures that an incoming current is I1, I2, let's say, and it knows that it current goes out, goes to some devices and so on. It should come back as the same current. So I1 should be equal to I2. It looks at that. If it's not the case, it breaks. That's what ground fault interrupter is. It breaks the circuit and protects any possible electricity hazard. This is another question very similar to the one we solved. In this case, the guy is stepping on the ground bare feet, very silly idea, and touching to a wired 480 volt. This time his other hand is not touching anywhere, so the current cannot go across, but his feet are touching to the ground, so the current go as shown. So I'll leave this up to you folks to send the current this way. You could also choose this way. It would be the same. We choose this way. We'll choose a path that easily it will go, and that's the path shown in here. And the question is asking us what is the current through the body. So you guys will find R total, and then use that to find, let's call this I total, delta V over R total, Ohm's law. And delta V, again, we have high voltage here, right? We high, and we have low voltage here on the ground. So it's again is like a power supply he is connected to, and delta V would be equal to 480. He doesn't have boots, so I put this picture here symbolically, but he doesn't have boots, no protected boots. So as you do that and solve the question, I'll give you the value you should find, and I'll let you folks solve it. The current you found should be 15 milliampere. So please solve this, go through it, and find the current. And the second part source asks if this will be large enough to feel or to be dangerous. Going back to our table, we will see that 15 milliampere is in the paralysis range of respiratory muscles, quite dangerous. You can always go back to this table to check what was dangerous and what was safe zone for AC current. Alright, see you on the next lecture.